First of all, I was talking about that exoplanet conference. The first one was called Exoplanets 1 in Davos, Switzerland. Then they had, cleverly, Exoplanets 2 in Cambridge, UK, and that was in 2018. Then 2019, they took a break. There simply wasn't one. And then 2020, Exoplanets 3, and that was done virtually on the internet. And now Exoplanets 4 came from Las Vegas, Nevada, my home state, and we're lucky to be hearing about anything that happened there in Las Vegas, of course. And like I said, we're happy to have Dr. Jessie Christiansen with us tonight. Jessie, hello.
Hi, everybody. It's a real pleasure to be here. Thank you for having me. So yes, let me tell you one story about Vegas, and I can tell you this story because it actually wasn't me. So I had heard for a long time, there was this legend of this physics meeting in Vegas, where the physicists had been asked to never come back again. And everybody thought this was apocryphal, like just a legend made up story. But just recently, I actually found the truth. So in 1986, the American Physics Society, the APS, had a meeting at the Grand M Resort in Vegas. Now, when casinos rent out their hotel rooms for people who are coming to a conference, they try to outbid each other because everybody wants this like group of thousands of people to come to their casino. So they offer the rooms really cheap, thinking they're going to make it back on the casino floor. So the Grand M did this. They put the rooms out really cheap for this big conference that came to town. It was the worst week they ever had, the worst week takings ever. And it's because physicists understand statistics, right? Scientists have a pretty good grasp on statistics. So like a roulette wheel, you don't have a good chance. So the physicists just didn't play. So the casino's whole ploy that they were going to make this money back on the casino floor did not pan out. So I won't tell any stories about this Vegas trip, but suffice to say, this is the first time physicists have been back to Vegas in a long time.
Wow, that's great.
Yeah, I wonder if a few of them were even counting cards. I know, or other means. Up at Santa Cruz, where I was a graduate student, they had in a glass case one of the shoes that they had implanted computers in, and they were actually tapping to the rate that the ball was going around on the roulette wheel, and they were able to bet quadrants and make money on that. They were calculating where the ball would fall on the roulette wheel. But I think they eventually did get caught on that one.
I see.
So we have exoplanets in store. I can't wait to hear what you're going to tell us about and the latest on the exoplanet front.
Yes. All right. So let me take it away then. I'm going to advance the slides, and it's working fantastic. So we did have a lot of really good fun exoplanet news in Vegas this week. And I'll discuss one brand new result right towards the end of the talk because it's very cool. And I was really excited when I heard it earlier in the week, and it's relevant to one of the planets I'm going to talk about. But the talk today is called Truth is Stranger Than Science Fiction. So let's get into it. Okay. So if we were in person, and I had a really fantastic time the previous time I gave a talk at Griffith Observatory, so I hope I'm back there in person one day. If we were in person, I would ask for a show of hands who recognizes this planet. And then I would give you a bit of a clue. I would put the Enterprise in front of it. This is Vulcan. This is Spock's homeworld in Star Trek. It's also known as Vulcan, Vulcanus A2, Navasa 2, or 40 Eridani A2. Now, the thing is, people have been thinking about exoplanets for a really long time, really long time. More than 2,500 years ago, the Greek philosophers were thinking about the idea of whether there were other Earths. Was Earth singular or plural? Were there many Earths? And Plato and Aristotle actually argued for the uniqueness of Earth. They said there's only one, there can be only one, the original Highlander, Earth. So more than 2,000 years ago, we're thinking about this idea. And at that point, it's purely hypothetical, right? Like these guys are still trying to work out what stars are, let alone the arrangement of a planetary system. But they're already thinking about whether there are other Earth-like planets out there. Now, in fiction, so that's in science. In fiction, we first start to see stories going off-world as early as Dante's Paradise in around the year 1300. So Dante kind of explores this story where different events in the plot happen in concentric spheres centered on the Earth, going outwards, Mercury, Venus, Mars, Jupiter, and Saturn. So he's like one of the first people that really starts taking fictional stories off world, just to be like, where else can we set our very cool stories? In the science side, a few hundred years later, we're in 1592, we're in the Renaissance. So in the Western world, the Renaissance is an incredible time for literature and art and science and math in the Western world. And there's this Italian mathematician whose name is Giordano Bruno, and I'm going to read this quote. There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. And I'll leave it as an exercise to my very educated listeners. In 1592, which 7 planets was he talking about? So not only did Bruno come up with this thought that there are countless Earths out there, he also very succinctly identifies the problem, which is that stars are very big and very bright and very luminous, and planets are not. Planets are much, much smaller and much, much dimmer. So when we're looking at the stars in the sky, we're blinded by the light from the stars, and it's very, very hard to see the planets. Bruno was eventually murdered, burned at the stake for saying, amongst other things, this thing about multiple worlds, because he was in Rome at a time when it was not good to say things against the Roman Inquisition. So he was actually burned at the stake. Thankfully, these days, as a planet hunter, I don't have to worry about that so much. Okay, back to fiction. In the 1600s, we see a novel by Mary Cavendish called Blazing World. This is an amazing work of fiction. And, one of the very, very first things you see where in the book, this boat goes through a portal basically at the North Pole and arrives in a fantastic world, like a brand new world, clearly a fictional world, not one of the planets of our solar system, but she's creating a brand new world. And that's super exciting to see that start to emerge in our science fiction and our fantasy literature. Over the next few hundred years, the 1700s, 1800s, 1900s, you start to see heaps of people explore this idea in their fictional stories of setting stories on mythical planets, not planets we knew, brand new made up planets. Okay, in science, so we're up to the 1950s. So we've had this idea for a long time that planets might exist out there around other stars. And Otto Struve, who's an astronomer, he suggests this idea. So what they knew about at the time in the 1950s were stars, binary stars. So 2 stars orbiting each other very closely. And in fact, the majority of stars are in multi-star systems. Most stars are in multi-star systems. So they knew about binary stars. And one way they could see these binary stars was if you looked at the light from the star and split it out and looked at different wavelengths of the light, you could see that sometimes the light was coming towards you and sometimes it was going away. And then it would come towards and go away, come towards and go away. And that's happening because these 2 stars are orbiting each other. And sometimes the star is coming towards you and sometimes it's going away. So Otto Struve has this idea. He's like, hey, what if we took one of those stars out and put a giant planet there instead? Maybe that's a way we could detect these planets by their gravitational pull on the stars and the measure of the starlight. Now, they'd have to be very close to their star, like these binaries that they had seen with periods of just a few days. So they orbited each other very quickly, just every few days. But it was conceivable that you could measure the light from the star wobbling because of this giant planet. Now, interestingly, at that point, the only system we knew with planets was ours. And our system doesn't have a giant planet right next to the star, right? We've got the 4 rocky planets that are close in, and then we've got the 4 giant planets that are further out. So a bunch of people were like, Otto, that doesn't make any sense. Like, you can't have a giant planet next to the star. There's no way for it to form there. It will just get swallowed by the star. That doesn't make any sense. So for a long time, this paper was ignored. So for the next 50 years, this paper has 7 citations. All right, in fiction, we move to the screen. So in the 50s, things start to happen in film. We have our first exoplanets, our first fictional planets appear on film. When Worlds Collide in 1951 and Forbidden Planet in 1956 are some of the earliest examples of films with exoplanets in them. And on TV, 1963, one of my favorite franchises of all time, Doctor Who, we finally see on TV on the small screen, they start exploring fictional exoplanets. That's very, very cool. All right. So 40 years after Otto Struve comes up with this idea that you could measure a starlight wobbling because of the gravitational pull of a planet, the very first planet is found orbiting a star like the sun with this method. And just a few years ago in 2019, the two Swiss astronomers who discovered that planet won the Nobel Prize in physics for this really incredible discovery. So in the first 40 or 50 years of Otto Struve's paper existing, it had 7 citations. Since then, in the last 2 decades, it's had over 100, as everyone's like, oh, dang, he actually called it. He said that these planets could be found if they existed, and it turns out they exist. So that was just like a very brief run through of the history of planets in science and science fiction. So let's move on a bit. Okay, so one of the things David mentioned up front is that I'm the lead scientist at the NASA Exoplanet Archive. So this is how NASA keeps track of all of the exoplanets that we found around the other stars, including the types of stars, the properties of the planets, basically anything we know about them. So one day we're putting in this planet a few years ago, 2018, and I'm looking at it. And if you're an amateur astronomer watching this, then you'll know that all the stars in the sky have multiple names, right? Like every few years, someone else comes along and is like, I have a better way to name all the stars, and gives them another name. So lots of stars, especially bright stars, have many names. So we were putting this system in the archive. It had 3 stars and 1 planet. And I'm putting in all of the names of this star. And you can see there's almost 20. But one of them jumps out, and it's 40 Eridani. And it kind of record scratches in my brain a little bit. And I'm like, what is that? And I wish I could tell you that I immediately knew what it was, but I did. I actually had to Google. I had to be like, why do I know this? Why do I know 40 Eridani? And that's Vulcan. That's the star that Vulcan, Spock's homeworld, is orbiting in the fictional movies and TV show Star Trek. So in real life, this 40 Eridani system has 3 stars. So you see the bright star on the right is A, and then it's orbited by a pair, a smaller binary pair on the left. So it's a triple star system. And we found a planet orbiting the A star, which is also the star in the fictional TV series that the planet is orbiting. So that is super cool. And, just goes to show when you use real names of things in fictional properties, eventually you might turn out to be true. So yes, did we find Vulcan? Well, in real life, the planet that's orbiting this star, 40 Eridani A, is not a rocky world in the habitable zone like Vulcan is in Star Trek. It's a very hot gas giant. Actually, it might not be a gas giant. It's a very hot, larger planet than Earth. So not quite. But one thing I'll say is that one of the very cool discoveries from the last 2 decades of planet hunting is that stars usually make more than 1 planet. And we might have been able to infer that from our solar system. So we have 1 sun and 8 planets, but we didn't know whether that was always the case. But it seems like if a star makes a planet, it often makes lots of planets. So 40 Eridani A, we might not have found Vulcan yet, but we found the system that Vulcan would be in if Vulcan existed. So that's pretty cool. One thing I did do was go through the archive and find the most Vulcan-like planet. So a planet orbiting a star most like 40 Eridani A that is most like Vulcan in size, so as rocky as you can get. So this is Kepler 62F. This is an artist's rendition of a planet that we found with Kepler that's orbiting a star called Kepler 62. I'm sorry, the names are all terrible. But this is the most Vulcan-like planet we have. That was a lot of fun. So I took it a bit further because I'm a giant nerd. So I went through the Memory Alpha Wikipedia article and looked at every single planet that had ever been name dropped in Star Trek from the start all the way through to Discovery. And there were 938 planets. From those 938 planets, I could reverse engineer that 51 of them were around real stars. And so I had to do a little bit of finagling. Like sometimes there'd be a planet around Taurus Alpha and I'd be like, well, there's no such thing as Taurus Alpha, but there is an Alpha Taurus. So I did a little bit of jiggling and I found 51 real stars. Then I went to the NASA Exoplanet Archive, and 7 of those 51 real stars actually host real planets in the real world. So there's at least 7 systems in Star Trek that turned out in real life to have planets. And there's one in particular that I'll spend just another minute on because it's delightful. This is Tau Ceti. So Tau Ceti in real life is a system that has 4 planets. It's a, the name Tau Ceti, you might realize it's actually a bright star. So here's the constellation Cetus, which is the whale, and there's Tau in the bottom, kind of middle bottom. And so in real life, it has 4 planets. The cool part is in Star Trek, it also has 4 planets. So the Star Trek episodes that talk about Tau Ceti are all taking place on Tau Ceti 4, and the planets are numbered 1, 2, 3, 4. So they even got the number of planets right, which is a lot of fun. So in real life, what is Tau Ceti like? So here's a comparison of Tau Ceti at the top to our solar system at the bottom. And you can see that, so the distances of the planets are to scale, but the sizes of the planets are not to scale. They've been scaled up so we can see them. The shaded green region is what we call the habitable zone. This is where if you had a planet like Earth with an atmosphere, you could have liquid water on the surface. And that's a really important thing for life, we think. So Earth has the solar system has up to 3 planets in the habitable zone, depending on how you count. And Tau Ceti has 2 that are like right on the edge, but they are actually quite a bit bigger than Earth. They're nearly twice as big. And that's where we start to get a bit worried that they're not rocky anymore, and they're more like mini Neptunes or mini Uranus planets. So we don't know if these could be habitable. So, it's life, Jim, but not as we know it. If there's life there, it's definitely at the extreme conditions of what we know. So I mentioned Kepler. Kepler 62 was a planet discovered by the Kepler mission. So this was NASA's grand experiment with putting a planet hunting instrument into space, and it went spectacularly well. I was lucky enough to be a staff scientist on Kepler for 4 years and got to participate in finding thousands of planets, which was really very cool. So I'll tell you a little bit about it. It's a 1-meter optical telescope. So this whole spacecraft that you can see here is about the size of a small van in space. And the goal of the Kepler mission, its main goal was to measure how common planets like the Earth are. So when I say a planet like the Earth, I mean a rocky planet in the habitable zone of a star like the sun. So that's 3 criteria that we need: rocky planet, habitable zone, star like the sun. So what did we find? We found lava worlds. So this is Kepler 10. It is a rocky planet the size of Earth, which is great. And it's orbiting a star like the sun, which is great. So that's 2 of the 3. But it has a period of less than a day. So this rock is right next to the star, and the surface is heated up to thousands of degrees. And what happens when you heat something up to thousands of degrees, it's made of rock, the rock melts, and you have this lava world. So is it Earth-like? No. But maybe Mustafar-like. We got lava world examples in fiction as well. Okay, so what else did we find?
Want to scream out, "I hate you!" But anyway,
I have the high ground. Okay, this is Kepler 22b. So it is orbiting a star like the sun, and it is in the habitable zone. So that's 2 of the 3, but it's too big. So again, this is just over twice the size of the Earth. So we don't think it's going to be rocky with a thin atmosphere like the Earth is. We think it's going to have some kind of much deeper, much thicker atmosphere like Uranus and Neptune. And in fact, when we look at planets like this, they seem to have the rough density of water. So it might be that it's something like a water world, which we don't have in our solar system. But we do have in fiction. We do have water worlds in fiction. And in fact, the very first one of these that was found was nicknamed Kevin by its discoverers because it could be a water world. All right. So what else did we find? This is Kepler 186f. So it is a rocky planet in the habitable zone of a star that's not like the sun. So we got 2 of the 3 again. So the star that Kepler 186 is orbiting is an M dwarf or a red dwarf. So it's much smaller and cooler and redder than our sun and puts out quite different radiation. Now, that doesn't mean it's not habitable, but it means we don't know. So a lot of the radiation that comes out of M dwarfs is high energy. So things like X-rays and UV, which are generally bad for life on Earth. There's reasons why you don't like to get X-rays a lot. And there's a reason why we invented sunscreen, because UVs are bad. So this planet might be sterilized by this high energy radiation coming out of the star, or it might be fine. Now, do we have any examples in fiction of a rocky planet in the habitable zone of an M dwarf? We do. So this is where Superman comes from. Superman comes from a rocky planet orbiting an M dwarf. And that's the whole point. When he comes to our planet orbiting our yellow sun, it's got very different radiation, and that gives him powers because it's so different from the light coming from his M star. So like, how cool is it that they included that little bit of astrophysics in the backstory of like one of the most famous comic book characters of all time? Anyway, so this is very Krypton-like. Now, have we found anything that satisfies all three? I feel like you probably know the answer is no. We would have heard about it. We haven't found any planets that are very Earth-like, like a true Earth twin that satisfies all three of those criteria: rocky, in the habitable zone of a star like the sun. And there are technical reasons why that happened, which if you're interested, you can ask about, and we can go into detail in the Q&A. But suffice to say, there's a whole slew of Earth-like planets in science fiction. Naboo, Caprica, Felucia, Beta Z, like all of the franchises have an Earth-like planet because that's the holy grail, right? Like that's what we're aiming for. If we found an Earth-like planet, we know that life has arisen on an Earth-like planet. So how exciting would it be if we could actually find another example? Now, interestingly enough, the fact that we haven't found any yet doesn't mean that we think they're rare. In fact, we think they're common. They're just really hard to find because they're so small and so far away from their stars, relatively speaking. So we actually think that up to half of the stars like the sun have a planet like the Earth. We just haven't found one yet. So we're getting there. We're getting close, but not yet. But we have found just a staggering array of super duper interesting planets that are even unlike anything we were trying to find when we were looking for Earth-like planets. So hopefully I don't get in trouble with copyright for showing this, but this is a classic scene. This is Luke Skywalker on his home world of Tatooine. And what you can see in the background is this classic, now famous binary sunset. Okay, so remember I said most stars are actually in these multiple systems, binaries or triples or higher order multiples. So when George Lucas did this, when he came up with this idea, this visual that Tatooine would be orbiting a binary star, super legit, totally fair. Could have happened. Did happen. This is an example. I think this is Kepler 16, which is the first planet we found orbiting a circumbinary, orbiting two stars, a circumbinary planet. And I really like this one because look, he even got the colors right. It's a G star and an M star. It's a yellow star and a red star. He didn't get the sizes right, admittedly, because red stars are smaller than yellow stars. But again, this is in the 70s. This is 20 years before we even found any planets, and 30 or 40 years before we found any orbiting two stars. So just like think about the prescience here to come up with this visual and even get the colors right. Super cool. Okay, so this is, someone asked previously about Dune. So Dune was a huge film that came out last year. And before that, obviously, was a huge series of books, very famous. So the world in Dune is called Arrakis. And the whole point of Arrakis is that it's orbiting Canopus, which is a known star in the sky. So, of course, I went and checked in the archive. No planets orbiting Canopus yet. What makes Canopus interesting? It's a red giant. So our sun, in 5 billion years, is going to become a red giant. It's going to finish burning up its hydrogen and helium in its core. Its core will collapse down into this little ball of carbon and oxygen. But in the meantime, it's going to spend a lot of time just like hanging out, getting big and bloaty and red and being a red giant. And then it's going to puff off all those outer layers into a beautiful planetary nebula for someone else to see billions of years after that. But in the meantime, it'll be a red giant. So we're going to go through this phase. Have we found planets orbiting red giants? Yes. And in fact, even going beyond that, now we have found planets orbiting white dwarfs. So remember I said, what will be left behind is this core of carbon and oxygen in the middle, surrounded by a beautiful planetary nebula. That core is called a white dwarf, and it'll just radiate away heat forever. I mean, that's honestly, our sun is just going to become a very small cooling ball of coal, basically, that just cools forever until the heat death of the universe. Sorry, that's depressing. Anyway, but what we have found is that planets survive the red giant phase. We've found planets orbiting white dwarfs. So that means that this phase that the sun goes through, which is going to last trillions of years as compared to the billions of years it spends as a like big glowing spark at the start of the universe, there'll still be planets, which is really exciting because that just like increases the amount of time we have for life to evolve by orders of magnitude, by 1,000 times. So that's pretty cool, the fact that we still know that there are planets around white dwarfs. Okay, This is a planet called 55 Cancri E. So 55 Cancri, another bright star, if you can't tell by the name, has a bunch of planets around it. And 55 Cancri E is another one of these lava worlds, like Kepler 10. But actually, it's around such a bright star that we were able to take more precise measurements of 55 Cancri E. And one of the things we were able to see was that it has a very high carbon to oxygen ratio. That means it has more carbon and oxygen than it would have if it was just made out of the same material as its star. So it's overabundant in carbon. So what happens when you take a lot of carbon and you heat it up because you're right next to a star and you crush it because you're in a rock? You make a diamond. So the headlines were very funny when this was first made, like, move over Tiffany's biggest diamond in the universe found, sort of thing. But this brings to mind, there's a planet in Doctor Who, again, I'm going to plug as one of the best franchises of all time. There's an episode called Midnight. It takes place on this crystalline planet. It's like a bottle episode. They get trapped in a shuttle and they're, being attacked from the outside. And it's about the stress of the situation and how the different characters handle the stress. It's a very cool episode called Midnight. If you haven't seen it, go watch it. But the point is, it takes place on this like crystalline planet with this like crazy radiation. So that's what this is. 55 Cranky E is this crystalline planet, possibly made out of diamond, possibly the largest diamond that we've found, at least. Okay. I think I'm coming up to the end of my fictional planets. So this is, and I'm going to start off by apologizing for the name. This is Ogle 2015 BLG 0051b. And again, I'm sorry. This is a planet that was found by microlensing. So microlensing is basically magic, but it has to do with relativity and the fact that everything with mass bends space-time. So you sitting there right now watching this, you're actually bending space-time just a little bit, but you're actually warping the fabric of space and time, which is amazing. Think about the power you have, warping space and time. So this, what we see is planets that go in front of background stars act like magnifying glasses. They bend space and time around them because they have mass, and they magnify the background star. So what we see is we're just watching the background star because the planet's too small to see. And what we see is that background star suddenly get brighter and then suddenly get fainter again. And you can deduce from the amount of brightness and the length of time it gets bright for, the size and speed of the object that's actually going in front of it. And then you can actually say, oh, it's a planet. And often there's a star there as well. It's very cool. Anyway, so skipping franchises one more time, we're going to go to the Marvel Cinematic Universe. You may have heard of it. So there's a whole arc with the Infinity Stones, and the Soul Stone is on a planet called Vormir, which is described as being at the center of celestial existence. So for us, that would be the middle of the Milky Way galaxy, right? The center of celestial existence. So the thing about microlensing planets is the best way to see them is to look towards the galactic center, because what you want to do is maximize the number of background stars where you could have this coincidental alignment of a planet in the meantime and a star in the background. So all these microlensing surveys are towards the galactic bulge, the center of the galaxy. So this system, Vormir, is 26,000 light years away, this Ogle 2015 BLG 0051b. 26,000 light years away. This is the furthest away planet that we've ever found. So the center of the Milky Way galaxy is about 30,000 light years away. So this is 90% of the way to the center of the galaxy. And it's the far and away the furthest planet that we found. So this is as close as I can get to the center of celestial existence, to Vormir, the Soul Stone planet. Okay, so that was a rapid fire tour through hopefully one of your favorite franchises. And now I want to talk about just a couple of real planets, because real planets are also pretty cool. One of the things we found that isn't Earth-like, but is super interesting, is planets in resonance systems. So resonances are where the orbital periods of the objects are related to each other with very simple mathematics, like one is 2 times the other, or one is half the other, that kind of very simple integer multiplication and division, very simple fractions. So we do have some examples of this in our solar system. So for instance, the Galilean moons of Jupiter, 3 of them are in a 1 to 2 to 4 resonance. So the inner one goes around 4 times, that's Io. For every 2 times, the next one goes around. And that one goes around twice for every 1 time the one after that goes around. So we see this resonance in the Galilean moons. And we also see that Neptune and Pluto are in a 3 to 2 resonance. So Neptune goes around 3 times for every 2 times Pluto goes around. So we do see these in our solar system. But what we've found around other stars are compact series of planets in very long chains of resonances. So this is a system that I really love called K2-138. And again, it's a garbage name, I'm sorry. It was found by the sequel to the Kepler mission called K2, and it was the 138th planetary system found by K2, K2-138. So it has 6 planets around it, and they were all found by citizen scientists. So that's people at home just looking through the Kepler and K2 data and helping us find planets. So I was lucky enough to be the scientist who was helping with this citizen science project and got to pull this one out of the discoveries and be like, wow, you guys found a really cool system. The cool thing about this system, besides the fact it was found by you guys at home, is that the 5 inner planets are in a chain of 3 to 2 resonances. So again, you know, the inner one goes around 3 times, the next one goes around twice. That one goes around 3 times, the next one goes around twice, all the way out, 3 to 2 resonances. Why that's cool is resonances are music, right? So things being related by integer numbers is intervals in music. It's tones, it's chords, it's frequencies. So this system is singing a song. And the wonderful people at System Sounds actually turned this into a song. I'm going to see if this starts, if I click on it. Yes, all right. Now everybody just listen. Okay, there we go. Now what's happening is every time a planet goes in front of the star, it makes a note. And the frequency of the note, the pitch of the note, how high the note is, depends on how fast it's going. So the inner planet is the one making the highest, most constant note. And then it goes out and out and out to the outermost planet, which is making the low note that just happens occasionally. And the reason it sounds pretty, the reason it doesn't sound discordant or out of tune, is because the planets are in resonance. They're all in this 3 to 2 resonance, which means it's musical. So that's your moment of Zen. And I want to invite anybody listening who's interested to go to planethunters.org, which is our citizen science project, current citizen science project to find planets using Tess data, which I'm just about to talk about. And you too could find your own planet. And then, you know, my favorite part is I get to put the citizen scientists on the papers with me. So you get to be in like a published refereed astrophysics paper in a journal and, you know, work with the scientists and get your planet published. It's super a lot of fun. I really like it. So please, if you have bandwidth and you're interested, go to planethunters.org and start looking through the Tess data. So I'm going to finish by talking about Tess. So Kepler operated for 4 years as in its original mission, and then 4 years in its follow-on sequel mission called K2. But in 2018, Kepler ran out of fuel. It couldn't run anymore. Luckily, in 2018, NASA launched Tess, the Transiting Exoplanet Survey Satellite. And that's this thing you can see here. So instead of being one big 1 meter telescope, Tess is 4 small 10 centimeter telescopes. That's 4 inches. If you're an amateur astronomer watching this, you probably have a bigger telescope than the telescopes on Tess. These are 4-inch cameras. And the point is, where Kepler did a very narrow, deep survey, so looked at one patch of sky quite deep to faint stars, Tess is doing an all-sky survey, looking over the entire sky at all of the bright stars. And I kind of hinted at this earlier, but with 55 Cancri E, the reason we know more about it is because it's orbiting a bright star, and we can learn a lot more about this system just because we're so much closer to it. We're getting so much more light from it that we can do more with. A lot of the Kepler targets that we found are quite faint, and it's just hard to do a lot more with them, like measure their masses and starting to measure their atmospheres. So the point of Tess is to look at the whole sky and find all of the brightest planets orbiting the brightest stars so that we can study them in a lot of detail with our upcoming missions, like the James Webb Space Telescope, which just launched, and in the future, a big direct imaging flagship that we're planning to launch in like 20 years. We'll be studying these planets. So that's what I have. Exoplanets are cool. Fictional exoplanets are even cooler. Thank you so much, and I'm happy to take questions.
Awesome. Wonderful job there. We really appreciate all this insight into exoplanets, and going through the science fiction ones is just great fun. We have had some great questions in the chat. First of all, someone is watching from Melbourne, Australia. Just thought you might appreciate that.
Hi, Melbourne.
So some folks wanted to know that there was an announcement that I think we're going to talk about later in the show as well, that they're hoping to send a mission to Uranus. and they were mentioning that that mission might help us learn about exoplanets. What do you think we could learn by studying Uranus about all those Neptunes and Uranus and mini Neptunes that are out there? I know they're the most common size exoplanet, but what would we learn?
Yeah, so one of the things that's interesting about Uranus is that it's tipped over, right? So a lot of the planets, when you look at them, they're all rotating and they're all orbiting the sun, but they're almost all roughly in the same plane. So Earth has a bit of a tilt, which is why we have seasons, because sometimes the northern hemisphere is pointing towards the sun and sometimes the southern hemisphere is. But Uranus is like tipped all the way over. It's like rolling around the solar system. And so there's a lot of open questions about planet formation and migration and evolution. So for instance, I said we found these Jupiter-sized planets right next to their stars, which is what Otto had predicted. But we're still trying to work out how that happens. You know, do you have to form it further out and then migrate it in and then stop it before it migrates all the way into the star, right? Like you've got to bring it in a certain way, but not so far. And how do planets interact with each other? So one suggestion is that these hot Jupiters get there because they exchange energy and momentum with another planet and send that other planet out while they go in. So conservation of momentum. And that might end up creating things like Uranus planets. Like, how do you tip something over? Do you have to hit it? Do you have to, change its spin somehow? So going out there and trying to learn more about its structure and its composition, like how differentiated is it? Does it have a core? Does it have a deep ocean? Does it have a deep atmosphere? We just know so little. So getting out there and actually doing that would be so cool. There are definitely things we can learn by looking at Uranus.
Wow. Excellent. Another person wanted to know, have we found any exomoons, and do we expect to?
That is a wonderful question. We have found 2 candidate exomoons. So I didn't really talk much about how Kepler works, but Kepler uses the transit method. So not the wobble method that Otto Struve suggested, and not the microlensing, which I talked about. So the transit method relies on the fact that if you have a planet orbiting your star, sometimes it blocks some of the light. So if you just measure the brightness of the star over and over again with time, if the planet goes in front, you see a little dip in the brightness, just like less than 1% dip, but you see this dip. Now imagine that planet has an even smaller moon around it. And so if the planet and the moon go in front of the star, then the dip might have a little tiny dip next to it, or the dip might be a bit misshapen because it's, instead of one circle, it's like 2 circles that are slightly overlapping. So you can imagine, the difficulty we have in finding things the size of the Earth and then take that down to things the size of the moon and smaller. It's very hard. It's a very, very, very precise measurement we need to make. So far with Kepler, which is the most precise thing that has ever been used to measure light curves, we have 2 examples of transiting planets where we can see some weirdness in the shape of the transit, and it could be because of a moon. So 2 candidates, nothing confirmed yet.
Okay. I know someone I think it was on Facebook, or someone had asked me, it was Twitter, wanted to know how we can characterize the atmospheres of these exoplanets, and I'll further it a little bit. How will Webb be able to do that?
Yeah. So there's really 2 ways we look into planet atmospheres. So the first is using that transit method, which I just described. So if you're a planet with an atmosphere and you go in front of the star, then the starlight, which is getting blocked by the solid part of the planet, some of the starlight goes through the atmosphere of the planet. Now, the molecules and atoms in the atmosphere absorb light at different wavelengths. So for instance, when we have clouds in the sky, water's absorbing and the light's not getting through, right? Like the clouds stop the light. So whatever's in your atmosphere is going to affect the starlight going through. And interestingly, it's going to absorb starlight at different wavelengths, depending on what the molecules are. So what you do, this is really cool. You look at the transit in a bunch of different wavelengths, and you map out how the size of the planet changes with wavelength, because at wavelengths where the atmosphere is absorbing, the planet will look bigger. Because the atmosphere is opaque, it doesn't let the light through. But at wavelengths where the atmosphere is transparent, like none of the molecules are absorbing, the planet looks smaller. So you actually map out the size of the planet as a function of wavelength. And that tells you where are things absorbing and where are they transparent. And then it's like a fingerprint. Certain molecules absorb at certain wavelengths and certain don't. So you can actually just like map that to your knowledge of molecules and say like, this has to be carbon dioxide because it's absorbing here and here. So that's how we actually map out the molecules and atoms in transiting planets. The other way we do is a detection method I haven't talked about yet, which is direct imaging, which is basically what it sounds like. We use a very fancy instrument to like block out the light from the star and look around that for planets that are kind of self-luminous. They're emitting a little bit of light. So again, it's very hard because planets don't emit a lot of light. But if you do find them, and most of the ones we found are much bigger and much hotter than the Earth, so they're radiating out a lot of light, you can actually take that light directly and spread it out and look for molecules and atoms. So that's the two ways. So looking at transiting planets or looking at direct imaging planets.
Okay. One person wanted to know if there's any evidence for planets having been moved outward, kicked out by migrating hot Jupiters. Do we think we've seen anything like that?
So there's a few examples we have. One of them is called free-floating planets. And that's exactly what it sounds like. We have found planets just out there floating between the stars that don't seem like they're gravitationally bound to a star anymore. And one way that can happen is that we can see these free-floating planets is if they get kicked out of a solar system. So for instance, one of the theories about how our solar system formed actually suggests that we started with 5 giant planets, and that, Jupiter, Saturn, Uranus, and Neptune survived this like early dynamic part of the solar system, but the 5th one got kicked out. So there could be this like whole population of planets just out among the stars that just got kicked out of their various systems. Now they're all just hanging out like cool kids club, like they're rejects, like, yeah, we're just out here. The other thing we see, so for instance, I was talking about, how do we get hot Jupiters? It seems like stars that have single planets very close in, that probably had to have something kick them in, we do seem to see a higher rate of companions around those systems. So either substellar companions like brown dwarfs or small stars. It seems like these systems that have these close in planets have a companion, and that exchange of momentum and energy with the companion could have been what migrated this thing in. So that companion got pushed out while the planet came in.
Okay, someone wants to know, where are the aliens? So I'm going to change that a little bit and say, where do we expect to find them? Because we can't say where they are for sure, but where would you look?
Yeah, so actually I forgot to say it, but one of the really interesting things that came out of this meeting in Vegas is we've been thinking for a long time about biosignatures, right? So this is, what would you see if you looked at a planet that had life? If you were an alien looking at the Earth, how would you know that the Earth had life? Like if you took the wavelength of the light and broke it out by wavelength, is there any feature that you could point at and be like, that has to be life? So for instance, on Earth, we have the vegetation red edge. So, in as much as the plants around you all look green, if you could see in infrared, plants are actually very infrared. They're very bright in the infrared. We just can't see that because we don't have eyes that see in infrared. But when you look at the spectrum, when you look at the light that comes off the Earth, you see this edge, this like cliff in the infrared because of the vegetation. So that's, for instance, a biosignature. That's a pretty complicated biosignature. So you're talking about chlorophyll and like a very complicated life form that uses that exact energy pathway. So it's very specific. So is there anything simple you can look for that indicates that there might be life? And oxygen, for instance, on Earth's atmosphere, most of the oxygen that's there now came from billions of years of single-celled microbes and bacteria creating oxygen and slowly changing the bulk properties of our atmosphere to having oxygen in it. But it's not necessarily on its own a biosignature, because there are geological processes that can create oxygen. So one of the cool things that came out of this thing in Vegas was this kind of emerging consensus that maybe a good biosignature is the presence of carbon dioxide and methane at the same time. So there are geological processes that cause carbon dioxide, and there are geological processes that cause methane, but they don't happen at the same time, and they should react with each other in the atmosphere and cancel out's the wrong word, but they shouldn't both survive in the atmosphere. It's a sign of what we call disequilibrium chemistry, that something's out of whack. And one thing that could make something be out of whack is life. The whole point of life is to throw things out of whack, to use energy in different ways and output waste energy in different ways. So this is a cool thing. The reason it's cool is because Webb, the James Webb Space Telescope, should be able to see those molecules. The wavelengths that James Webb looks at, which is in the infrared, cover a lot of the important lines in carbon dioxide and methane. So if this is a legit, robust biosignature, which is still out for debate, but there's emerging consensus, more and more people are like, that could work, then it's something that Webb could measure.
Okay, that's great to hear. Very, very excited about that. A lot of people wanted to know about the aliens. Well, I think we need to wrap up the questions at that point because we need to move on with the rest of our show, but we could talk exoplanets all night. And we're going to have to have you back in person.
Yes, I'd love that.
As soon as we're doing shows in person again, maybe we'll do a special exoplanet only night or something like that. Have fun with it. So thank you so much for joining us. It's been a huge pleasure. Absolutely. Yes. And just amazing time here talking exoplanets with you.